Okay, so in the previous class we had studied about the JVM, how it works, or rather how a program runs internally. So let's do a quick revision first. So what happens is, as a programmer, you write the source code, which is the .java file that you usually write. And the source code is passed on through a compiler, which does nothing but translates the .java file to an object file or object code. So the source code that you write, that is compiled by the compiler, and we get the object code which has an extension .class. This is also known as a .class file. Now what happens is, this particular portion falls under the compiler part. So this particular job, or this particular section of executing a program, falls under the compiler part. Now once you have the object code, this goes to a class loader. So the object code now is fed to a class loader, which loads the .class file. Then again, once the class file is loaded, there is a bytecode verifier which verifies the bytecode. Now once the bytecode is done verifying, so once the bytecode is completely verified, it goes to the interpreter. As you can see, once the bytecode is verified, it goes to the interpreter. And this is where the actual program starts running. The program actually starts running here. So the bytecode is sent to an interpreter, and the interpreter executes the bytecode. There are certain other parts as well that are involved in executing the bytecode, so you do not need to worry about them. So this particular portion, starting from the class loader up till the execution of the bytecode, this is the JVM. So this is what we call the JVM. So there are two parts: compilation, then there is the interpretation part. The compiler part is separate from the JVM. It happens with the help of a compiler, and it generates an object code. The object code is then, the JVM works upon that object code. So the class loader loads the code, bytecode verifier verifies the code, and then it is interpreted and executed by the JVM. Now, we have heard, while studying Java, we have always come across the term that we have always come across this statement: Java is a platform independent program, or rather programming language. Right. So we have heard this many times. Java is a platform independent programming language. Now, what does this being platform independent mean? What does it actually stand for? Normally, when we write, let's say, let's consider a different programming language, let's say C, the C programming language. So what happens is, normally the programs that you or other students write, those programs are very short. They just contain, let's say, a maximum of 100 lines. If it is a very big program, it will have a maximum of 100 lines. But normally, let's say I've designed a video game for the PC, and rather I have designed a video game. Let's not say for the PC. I've designed a video game and there are certain lines of code. Now, designing a video game will have, a lot of work put into it, and the number of lines of code in that game code will be much more than the programs that you normally write. So, let's say I have a game, and there are there are thousands and thousands of lines of code. So let's say there are these many lines of code, and the game is written in using C programming language. So what happens is, since C programming language is not platform independent, so let's say I am a programmer. I have written these many lines of code and I have designed a game. Now I give you the code of the game and ask you to run it and see if it is working well and fine. So I give you these many lines of code. And what happens is, let's say you are running Windows 7. What you would have to do is you would have to compile this unit, tens, 100,000, 10,000, lakh, 10 lakh. So about 10 lakh lines of code. So you will have to compile these 10 lakh lines of code to get a .exe file. So so let me write it down. So you'll compile this to get a .exe file. So um, this is the extension of the executable files that are supported by Windows. So you'll compile these many lines of code into .exe, and then you will be able to install the game and then play and give me a review of how it's working. Now let's say I have another person. That person uses Mac OS. So he'll again compile this whole thing from the start, and he will get, let's say, a .app file. Let's say this is the extension in macOS for applications. So he'll give a .app file. He will install this .app file, he'll play the game and then tell me and then give me a review of how it's working. But the problem lies in this step, the compiling step. Normally the programs that you and I write have very few lines of code. So compiling them multiple times does not, pose that much of a headache to the person who is doing it. But let's say you are going to compile 10 lakh lines of code, or even there could be even more lines of code if it is a high graphics game. What will happen is it will take up a lot of time to compile these many lines of code, right? So every time you change the OS or the platform, you would have to compile this once more. You'll have to generate the uh, file corresponding to that particular platform or operating system, and then you can run the particular game. So that's a bit problematic. So let's say I'm using Android. So let's say I have given to another friend who uses Android. He will again have to compile and generate a .apk file, which he can then install on his mobile and then run the game. So this compiling step is, time consuming. It's very time consuming when you have uh, many lines of code. So Java, what it does is this platform dependence. The C programming, something written in a different language which is not platform independent. What happens is in every platform you would have to compile it before running it. But Java overcomes that problem. It is platform independent, which means that you do not need to compile it every time. In Java, what happens is, so in Java, you compile once to get bytecode. So in Java, what happens is, how does Java overcome that platform dependence? In Java, the mechanism, the procedure of running a program is such that you compile once to get the bytecode. So this is an intermediate form of a code. So this is an intermediate form which is platform independent. So bytecode runs on any machine, platform independent. So I can take this piece of bytecode. Let's say I have that game. I've written the game in Java. Game written in Java. So I have compiled. So I've compiled 10 lakh lines of code. And I get an intermediate file that is called a bytecode file. This particular file is platform independent. Let's say I'm giving you the code, so you run Windows 7. So I give you the bytecode. You will just have the JVM for Windows 7. You have the JVM for Windows 7. You feed the bytecode. So you feed this bytecode and then it is executed directly without the compilation step. So this step is skipped. Maximum time that a program takes, is during the compiling time. When the program is getting compiled, that's the highest time that it will take. Once it's compiled, it's done. It runs very, fast and very efficiently. But this compilation takes a lot of time. So Java, what does Java do? It uh, skips this step. So it does this just once to generate a bytecode file. Now, if I have Mac OS, he'll use a JVM for Mac. He'll run the same bytecode and execute. Let's say I have Android. He will again have the JVM for Android. So he'll have the JVM for Android installed. He'll run the same bytecode and execute. So this particular process is much faster compared to compiling from scratch. So compiling the whole thing from scratch or from the beginning is more time consuming than using this particular format. So that's how Java achieves platform independence by using a bytecode file instead of directly converting it to exe. So here I'll get a .exe after executing the bytecode. Here I'll get a .app file, and here I'll get a .apk. Okay, this step is skipped. This whole thing is skipped. I directly work upon the same bytecode for all the platforms. So I have the same bytecode for Windows 7, same for macOS, or same for the Android. And I just, you know, run them using the corresponding JVM for the particular platform, and I get the corresponding applications for those particular platforms. This whole process is much faster. Now, what does a compiler actually do? So, what is the role of a compiler? Let's say they ask you a question, which where you have to answer what is the role of a compiler. So to put it simply, let's say you are watching a Hollywood movie. So when you watch a Hollywood movie, let's say you are watching a Hollywood movie which has subtitles. Now, what is the job of this? The subtitles, what does it do? It helps you understand in a language which you are comfortable with. So, what is the use of subtitles in a Hollywood movie? It helps you understand in a language which you are compatible with. Nowadays, we also have dubbed movies. So, that dubbing, what happens is, or say, let's say it could have subtitles or it could be dubbed in Hindi. So, it could either have subtitles which you can read and understand what's going on in the movie, or you could have the whole movie dubbed in a different language, the language that you are comfortable with. So this dubbing or having subtitles is synonymous to, the job of a compiler. So a compiler translates high level code to something that is understandable by the machine. So compiler is nothing but a translator. So what it does is it translates high level code to something understandable by the machine. In Java, this is a two-step process. So it translates into bytecode, which is then interpreted in other languages. It directly translates to the machine code. So normally, when we write programs, we write certain lines. So these are English-like words: public, static, void, main. So these are English-like words. So this is what is known as high-level language. Okay, why is it called high level? Because it is understandable by humans. Humans can understand by reading these words, so it's called a high level language. It's more like English language. After compiling, it is converted to bytecode. which is a series of, let's say, zeros and ones, and so on. So this is understandable by a machine. So machine understands nothing but zeros and ones. So understandable by machines. So this is also known as low level language. Why is it called low level? Because it is difficult to understand. If a human reads a string of zeros and ones, it's very difficult to make out what exactly is written. So you can't look at this and say that public static void main is written by looking at this line. So that's why it's called a low level language. So just remember the the method or the language that we use to write the programs, they are called high level language. The job of a compiler is to convert this high level language to low level language. That's the job of the compiler, so that the machines can understand. So the compiler acts as a translator, just like in Hollywood movies, you have subtitles. So the compiler is similar to the subtitles in a Hollywood movie, wherein the compiler helps the machine to understand something and the subtitles help you to understand what is going on in the movie. So remember it in that way. A compiler simply translates it into machine understandable code so that the machine has no problems in understanding what you have written. Now, let's come back to today's topic. So, and also before that, you know, before we move on to JRE and JDK, the full form of JVM. So JVM is an acronym for Java Virtual Machine. Now, why is this term virtual called? Why is it used? Why is it called virtual? So there's a reason behind it. This particular JVM thing is not a physical machine just like a computer. Okay. If you take the example of your computer or the desktop or a laptop or a mobile phone, whatever it may be, it's actually physically present there to, do stuff like, let's say, if we take the example of the cell phone or the mobile. So it's a physical thing with which you can do a lot of things. You can call, you can watch videos, you can do stuff like that. But JVM is not. You cannot say that. You cannot go to your friend and say, "Take a look here. I have a JVM." Okay, it's not a physical thing. You just can't say. You just can't go to somebody and say, "See, I have a JVM in my hand," and you know, it's not a physical thing. You cannot see it. It's something. It's type of an abstract thing, so which means it's virtual. And what happens is, to understand it much more, easily, consider a picnic. So you have been to picnics. So consider this particular event. So this is an event. A picnic is an event where everybody comes, eats, has fun. So what happens is, a picnic is not a physical thing, as in, let's say, there are three friends. So let's talk about the food that we eat in a picnic. So let's say there are three friends. You do not actually have a place called picnic where the food is readily available and you just go there and start having, just like a hotel where. So if you take a hotel as an example, where you go, you order food and you get it served, but it's not like that. Picnic is, let's say, the friends decide to cook one food item each and then have a picnic on a particular day somewhere. So X cooks something, Y cooks something, Z cooks something, and then together you collect those. So you meet up. So XYZ meets up at a place, and together they, you know, sit around, and eat whatever they have brought, and have fun. So JVM works somewhat in a particular fashion, in that particular fashion. So JVM has certain components. It's not a physical machine that's actually present. It has certain components. So let's say there are X, Y, and Z components. So they together, X does some work, Y does some work, Z does some work, and together they help to execute the program. Just like in a picnic, there are, you know, each and every friend brings his or her own cooked food, and then everybody shares that food and has a picnic. Just like that, a JVM has certain components. It could be any number of there are fixed number of components. You do not need to know the exact components, but let's, for the sake of understanding, let's say the components are X, Y, and Z. So X does something, Y does something, Y does a piece of work, and Z does something. Together, what they do leads to execution of the program. So together, what the component, each of the components does some little work. So together, all that work translates to executing the program. So we have talked about two components. The class loader is a component. It has a particular job, which is load the class. There's a bytecode verifier, which is also a component. So this is also an example of a JVM component. So it verifies bytecode. That is the job of the bytecode verifier. So it verifies bytecode. There are certain other components which do certain other jobs. So in total, each and every component does a little bit of something, and together they helps execute the program that you have written. So that is why Java is called a virtual. So this JVM is called virtual because it does not physically exist as a single thing. So it does not, JVM is not a single thing. JVM does not exist physically as a single component, such as your mobile. So your mobile is a single entity. You know it as a mobile. It's a single thing and it does things for you. JVM is not like that. There are certain components that work in certain ways. We call those components together as the JVM. So it's an virtual concept. There's no physical thing called the JVM. There are components. So this is an actual application, small application. This is also a small application. So these particular applications or components together, they are known as the JVM. Now let's move on to the difference between JVM, JRE, and JDK. So JRE stands for, so here, JRE is an acronym for Java Runtime Environment. So it provides a runtime environment where it is a set of software tools which are used for developing Java applications. So let's say I have the JVM, I have certain, so I have a set of libraries. Let's say libraries are nothing but the already available classes that you normally use in your programs. So I have a set of libraries and certain other files. So JVM in itself has certain components inside. Those together with the set of libraries and certain other files, they make up the JRE, or the Java runtime environment. So together they make up the Java runtime environment. And what is JDK? Again, it's kind of like set theory where, take a look here. So JVM can be said as a subset of JRE. So JRE consists of the JVM, a set of libraries, and certain other files. So these are the components of JRE. So JVM is a component of JRE. The set of libraries is a component, and the other files, there are certain other files which are the components of a JRE. Now let's take a look at JDK. So what is JDK? Again, so JDK stands for the Java Development Kit. So JDK is the acronym for JDK is the acronym for Java Development Kit. It has the JRE as a component and development tools such as the Java compiler, the Java interpreter. So this is the Java compiler. So this is the so this is the compiler, and this is the interpreter. Okay, so together this whole thing, the JVM, so the JVM, the set of libraries, the other files form the JRE, and the JRE together with the development tools form the JDK. Okay, so that's all about JVM, JRE, and JDK. Now let's move on to basics. So let's talk about the Java data types quickly. So take a look at this chart. So this is a compact, representation of the data types in Java. So data types can be primitive or non-primitive. Primitive are the ones that are available, the default types that are available with Java. So Boolean is a primitive data type, and there are numeric types. Under numeric, there are characters, and there are integral data types. So under Boolean, there is the Boolean type. Under character, there is char. Under the integral part, there is the four types of integers. There are the four types of integers and floating point. So the four types of integers are byte, short, int, and long. You already know that. And the floating point is float and double. So that's the classification of the primitive data types. So this whole part is the classification of the primitive data types, and this part is called the non-primitive data. So strings are an example of non-primitive data types. Arrays are an example of non-primitive data types. There's something called an enum, which is also a non-primitive data type. We do not have enums, but we will be learning about strings and arrays. So in this particular class, we will be covering these two topics, strings and arrays. In, in the coming classes, we'll cover these two topics. But just remember this particular chart. So data type can be subdivided into two types, the primitive type and the non-primitive type. The primitive type has Boolean and numeric. So Boolean has just one, the Boolean data type. Numeric has two subtypes, the character and the integral parts. Character again has the char data type, and the integral parts can be integer or floating point, depending on. And the integer has four parts: byte, short, int, and long, and floating point has float and double. So that's all you need to remember. Apart from that, there is one more thing: the default values and the size. So this is also a table that you will have to memorize. Probably you had memorized it in the previous class as well. So Boolean has a default value of false, and the default size is 1 bit. Character has a default value this, and its default size is 2. Byte has a default value of 0, and its size is 1 byte. Short is of 2 bytes. So the integer parts have default values as 0. Only the long integer part has an suffix of L, which denotes that it is a long integer. Correspondingly, the size also double as we move down. The float has a suffix F and is of size 4 bytes, and the double has a suffix D, which has 8 bytes. So its default size is 8 bytes. So long and double have the same size. Float and int have the same size. Char and short have the same size, and Boolean and byte again have the same size. So you could also try and remember it in that way. So Boolean and byte will have a size of 1 byte, char and short will have 2 bytes, int and float has 4 bytes, long and double has 8 bytes. Also, you need to remember the default values. This is important, this value is important. So this particular value is important. This is also important. They often try to confuse you during exams. They'll ask short questions depending on this. So Boolean always takes a default value of false. Now, why does character use 2 bytes in Java? And what is this thing exactly? So as we know, Java uses the Unicode system. So to achieve platform independence, so Java to achieve platform independence uses converts things into bytecode and uses Unicode for encoding purposes. So before before a Java program is So Unicode is nothing but what's contained inside the bytecode. So the bytecode file contains Unicode characters. So this bytecode file that is generated after compiling contains Unicode characters, and that is further converted to, so it's not exactly 0 and 1. I had said 0 and 1 for reference purposes. So bytecode normally has Unicode characters. So these Unicode characters are then converted to machine code. 0, 1, 0, 1, 0, 0, etc. using the interpreter. Rather, by the JVM. So why does, so they may ask you the question, why does character have the default value of this? So this is the lowest range in the Unicode. So this value is the lowest range of Unicode system. That's why the character has a default value of this, and the size of character is 2 bytes because Java uses something called UTF-16 instead of UTF-8. So 2 bytes is equal to 16 bits. So each bit corresponds to a particular symbol. Okay. So each bit corresponds to a particular symbol. So this is 1 bit, this is 1 bit, this is 1 bit, and so on. So 1, 2, 3, 4, 5, 6. In this case, the lowest value uses 6 bits. So there's no need to go into detail. Just remember Java uses UTF-16. That's why character uses 2 bytes, because 2 bytes is equal to 16 bits. Now, why does Java use the Unicode system? So there's a very good reason why Java uses the Unicode system. So previously, before Unicode, there were many language standards. So there was the ASCII standard, the ISO standard, the KOI 8 for Russian, and so on. This caused particularly two problems. So particular code value corresponded to different letters in various language standards. So the ASCII value of A, rather not, let's not take A, it will confuse you. Let's say a symbol, let's say the dollar sign. So it has a different code in the ASCII format. It has a different code for the ISO format. It has a different code for KOI 8 and so on. So every language standard had different codes for one single symbol. So that was very problematic. Let's say a programmer in the United States writes a program. That program is shipped to a European country where they use ISO format. Now there was some problem, between the intertranslation of the program code. So USA uses ASCII, so the ASCII had to be translated to ISO. That was, troublesome work. So a particular code value corresponded to different letters in various language standards. So there was no unified standard. Different countries use different standards. That posed problems, when interchanging codes. And the encoding of languages with large character sets have variable length. So some common characters are encoded as single bytes, other require 2 or more bytes. So the encoding was not uniform. So there are 2 points. Simply put, so before Unicode, There were many language standards, or rather, let's say, so the mouse is creating some problem, some unknown problem. So before Unicode, different countries had different language standards. So what was the problem for this? A program written in the USA which used ASCII had to be first translated to ISO used in Europe to run it on a machine in, let's say, Sweden, which is in Europe. So a program written in the USA which used the ASCII format had to be first translated to ISO format, which was used in Europe, to run it on a machine in Sweden. So that was extra work. Why would I do extra work? So this was one of the problems. The second problem was, let's say ISO used variable length encoding. So what does variable length encoding means? So let's say A uses 1 byte, a lot of A's will use 2 bytes, even more number of A's will use 3 bytes, and so on. So there was no particular standard. So single A used 1 byte, multiple A's used 2 bytes, more than that used 3 bytes. So due to this variable length encoding, this translation job became even more difficult. You see, there were no humans who used to sit and translate each and every line of code. So there were programs that used to translate these codes, but designing those programs became challenging, because different countries. So designing a translator program became challenging when different countries had different language standards and variable length encoding. So the main problem was that designing a translator program. So a program written in the USA would not run as it is in Sweden, which was in Europe. So designing a translator program to translate the USA program to a European program, so language to a European language, that became very challenging when different countries had different language standards and variable length encoding. So now the programmers, you know, after a lot of time, the programmers thought that there is a need for a unified language or unified encoding system. That's when Unicode came into being. So this particular problem led to the necessity of a standard. So Unicode is a uniform code with fixed length encoding. So uniform code, fixed length encoding. So the solution to this translator program problem was Unicode, wherein it was a uniform code designed to be followed all throughout the world, no matter where you are. And the encoding was also fixed length, so designing a translator program became very easy. So one of the many reasons for Java being a popular language was due to using Unicode as the encoding language or the encoding format. Because Unicode could run anywhere in the world. It did not depend on the country where you were running. Unicode was a standard that was followed later on, was a standard that was followed by each and every country around the globe. And that is one of the reasons why Java is so popular. It's platform independent, one reason, one big reason. Second big reason is that it follows the Unicode encoding format, which does not have need to have a translator program. These are two of the advantages for using Java and why it became so popular. So to solve these problems, the problems that I talked about previously, a new language standard was developed, that is the Unicode system. In Unicode, a character holds 2 bytes, so Java also uses 2 byte for characters. So the lowest value of Unicode is this, highest is this. So again, Unicode also has certain sub standards. So there is UTF-8, UTF-16. So we do not need to go into such details. Just remember, Java uses Unicode. If they ask you why Java uses Unicode system, you have to discuss about the problems that was there previously. So designing a translator program was difficult and challenging when different countries had different language standards and variable length encoding. That's when the solution to this problem was the Unicode system. So the solution to this problem of designing, a translator program, the solution to that was a new language standard as a whole, which is the Unicode system. That's all you need to know. Now let's move on to the next topic. So the Java if-else statement. So by now you already know how to write an if-else statement. I'll just revise the whole thing quickly. So I'll be drawing a flow diagram wherein it shows how the control flows. Okay, so I have a condition, if the condition is true, then something will happen. If it is false, then something else will happen. Okay, so If condition is true, so I'll execute if part. If condition is false, I'll execute the else part. And that's the end. So this is how you draw a flow chart or a flow diagram. So this basically explains the if else statement. So this is nothing but the if else construct, wherein if there is a condition, so if the condition is true, then execute the if part. If the condition is false, then execute the else part. That is how an if and else construct works. If I look at the code, sorry, if 5 is greater than 0, so this is 5, SOPLN, rather let's not use true, SOPLN 5, else SOPLN 0. So if you take a look at the code, so this is the condition, this particular part is the if part, this particular part is the else part. Okay, so diagrammatically the if else construct is somewhat like this. So if I have a condition, the condition is true, so it follows this path and executes the if whatever written inside the if part. If the condition is false, it will follow this path and execute the else part of the code. We also somewhat talked about the ternary operator in the previous class or in the previous standard. So what is the ternary operator? So the ternary operator works in a similar way. So consider that previous example of the code. If 5 is greater than 0, then SOPLN 5, else SOPLN 0. So if I write that using the ternary operator, so I'll have the condition 5 greater than 0. I'll have the if part, and I'll have the else part. So this is how a ternary operator works. So this is equivalent to the if part. So this is let's not say if part, this is equivalent to if, this is the if part, this is equivalent to else, sorry, and this is the else part. So it's a shorthand notation for if and else statement. The ternary operator is nothing but a shorthand notation of the if and else construct. So this is the condition. Okay, so I have a condition. If the condition is true, then I have the if part. So this is executed and this part is ignored. If the condition is false, then the if part is ignored and the else part is executed. So just just recall the previous flow diagram. It works in a similar way. If the condition is true, I execute the if part. Else, if the condition is false, then I execute the else part. So that single flow diagram, clearly demonstrates how an if else works or a ternary operator works. Both work in the same way. Let's move on to the next topic. So we have also learnt about the switch case in the previous standard. So the syntax of the switch case was switch and variable. Inside we had cases. So the value of the cases would be equivalent to the value of the variable. So if let's say this is an integer, so I'll have case 1. So 1 is a value of this particular variable. I'll have something, I'll have a break statement. Then I'll have the next case. Let's say 2 is a value. Again, 2, let's say 2 is a value of this variable, probable value of this variable. I'll have something written. I'll have a break place, and so on. And finally, at the end, I'll have a default, which is optional, but it's good to have. So I'll have this default statement, which will be executed if none of these cases are executed. So let's take a look. Okay, so let's again okay, let's just continue this switch case in the next class. So today we have completed up till the Java if else construct. So in the next class we'll be talking about the switch case, and we'll also be talking about loops. So once we finish loops, we'll try to start, I'll just try and explain arrays to you so that there's a certain thing in loops. So let's take a quick look. So inside loops, there's something called a Java for each loop. So this particular loop is specially used when we work with arrays. So we'll be talking about this in the next class.